Let's look at calculus with parametric equations. If we have, looking at the motion of a particle, this flying around, and x of t and y or t are differentiable functions, what are dx dt and dy dt? So dx dt, the rate of change of x with respect to t, t being in this case time. So it would be telling us how x is changing with respect to time, and so what that is the velocity of this fly in the x direction. And then similarly dy dt would be the velocity in the y direction. What if instead we were interested in a tangent to the curve at some given point? The slope of the tangent to the curve, if it's defined parametrically, is still going to be dy dx. So our dy dx can be obtained by taking dy dt over dx dt, provided dx dt is not 0. Now, if we were interested in finding horizontal tangents of a parametric curve, because a lot of times these are points of interest or helps us as we're getting this graph, when would it have a horizontal tangent? And if you think of a horizontal tangent, it would be when this slope was 0, so it would be when dy dt equaled 0. And if we were interested in where it had a vertical tangent, that would be when the dx dt equaled 0. However, if both dy dt and dx dt equal 0 at the same point, then I would have to do some further investigation to figure out whether it was horizontal or vertical. We're going to see an example of this following. So what if you're trying to graph it and you found some of these tangents and things, and now you're interested in the concavity. So concavity is second derivative, but it's second derivative of y with respect to x. So we want to be careful with that. And what we could do then is we could differentiate with respect to x dy dx. So we could use our formula for dy dx, and we could replace this y with dy dx, and so we'd need to replace this y with dy dx, and this dx dt wouldn't change. So when we want the second derivative with respect to x, let's look and see how we get that. We take dy dx, which could be found like this, and then we need to differentiate that with respect to t, and then divide that by dx dt. So we have to be careful. You may think as I'm just going to take two derivatives of y with respect to t, two derivatives of x with respect to t, and that does not equal the second derivative as shown here. This is how we would have to get at the concavity. Now let's kind of revisit this idea of speed. So if I'm looking at this particle that's moving along from t to t plus delta t, and I see how it changed here, I could compute average speed, because that would be the distance it traveled over time. And we could get that approximate of that as we look at this piece right here, which is just simply delta x squared plus delta y squared square rooted, and divide that by the change in time here, which is delta t, and this would give us the average speed. Now if we were interested in figuring out the instantaneous speed at a time, we could then take the limit as delta t approaches 0 to find that speed at time t, and this is nothing more than the definition of our derivative, and so that would equal the square root of dx dt squared plus dy dt squared. So if we would like the speed of this particle that is defined with these parametric equations, and x of t and y of t are differentiable functions of t, then the speed of the object is given by this expression. Now we're also interested in finding the length of a parametric curve, and we're going to go about that much like we went about finding the length of a curve when they were not defined parametrically. And so we would take this and divide this up into line segments to approximate what this curve was doing, and the length of any given line segment is simply going to be delta x squared plus delta y squared square rooted. And so we could sum up n of these and get an approximate for the length of this parametric curve. However, if we want these expressed in terms of involving our parameter t, something we can do is we can divide this by delta t t squared, and so we could put it underneath the square root and put it both terms here, and then here is a delta t here that would compensate for that fact, because essentially if we put on a delta t, this is dividing by square root of delta t squared, which is delta t. So this is just equivalent to a 1, so that's legal to do that. And then you can probably see where we're headed with this. We're going to take the limit as the number of these little line segments approaches infinity, and so that will equal the definition of our integral here. So we're going to integrate from our little a to b, where a and b were actually our values of our parameters. So t equal a and t equal b. And then we have the square root of dx dt squared plus dy dt squared, integrating that with respect to t, and we would have the length of this parametric curve. So let's look at an example. We want to find the length of a curve given by these parametric equations. And so we would say, okay, I'm going to integrate from 0 to 2 pi, and I'm going to have the square root of dx dt squared. So the derivative there is going to be negative 2 sine 2t. We got that 2 because of this chain rule. Then that needs to be squared, plus the derivative here, that's going to be 2 cosine 2t and squared dt. So as I compute that, this is going to be a 4 and this is going to be a 4. I could factor that out and square root it and bring it out in front of the integral completely, and it would look like that. And then this is just simply going to be the square root of sine squared 2t plus cosine squared 2t dt. But of course, there's the favorite trig identity. That's just a 1. So I just simply have to integrate dt here, or 1 dt. So that's just going to be 2t evaluated from 0 to 2 pi. So that's going to be 4 pi. But wait a minute here. This was the length of the curve, and this is a circle, but it's a circle of radius 1 because of these numbers right here are 1s. So if we have a circle of radius 1, we could have figured out the length of this. That's the circumference. Okay, so the circumference is going to be 2 pi r, and our radius was 1. So that's going to be 2 pi. Well, hold on a minute. We just computed it and got 4 pi. So what's wrong with this? And what's wrong with this is something that we have to be careful of as we're working with parametric curves, because I integrated from 0 to 2 pi, but as you look here, the period here is 2 pi over 2, or pi. So what happens from 0 to pi, if I start here, from 0 to pi, I actually trace out that circle 1 complete time, because you can see if I put pi in here, the cosine, I'd have the cosine of 2 pi, and I'd be back around. And then since I integrated to 2 pi, I actually went around that circle 1 more time. So I have to be careful about that when I put on my limits of integration. I don't want to trace out the curve more than once, because I actually figured out the length of this curve 2 times around, or the distance I traveled if I'd gone 2 times around, and so I got it 2 times higher than what I should have had. So I have to be careful about that. So if we have the curve C given by parametric equations x of t and y of t, and we have t going on the interval from a to b, where x prime and y prime are continuous functions on that interval, then and C is traversed exactly once. So we're going to have to be careful and confirm that. Then we can go ahead and integrate here. So what I needed to do on the last problem was just integrate from 0 to pi, because then I had traced the complete circle 1 time.